All right, here we are in chapter 5. So the first part of chapter 5 is just kind of about simulation. The whole chapter was about probability. The first part was just about randomness, probability, and simulation. You just want to understand here that the point of the book here is that chance behavior is unpredictable in the short run, but it forms a predictable pattern in the long run. The law of large numbers said that if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. So the probability of any outcome of a chance process is a number between 0, including 0, and 1, including 1, and it just describes the proportion of times the outcome would occur. So the law of large numbers says, so if I was tossing a coin a few times, my proportion of heads might not be exactly 0.5. But as I keep repeating this over time, I do eventually get to that 0.5. So that's just the law of large numbers, and that's the idea of probability that we follow as we go through this course. So there's some myths here. There's the myth of short-run regularity. So we know that probability is predictable in the long run, but then we try to think that it's going to be predictable in the short run. So like with a coin toss, we might think that if we toss the coin 10 times, we're going to get 5 heads. And if we see 7 or 8, we think it's unusual, and maybe it's really not. There's also the myth of the law of averages. So probability tells us that random behavior evens out in the long run. So future outcomes are not affected by past behavior. That is, past outcomes do not influence the likelihood of individual outcomes occurring in the future. So sometimes what we think, if somebody is on a streak, we feel that he's going to continue to keep doing well, but really his chances are about the same as they were in the first time he started his streak. We can also simulate things. When we simulated things in class, or if they ask you to simulate on the AP exam, they're probably going to give you the table. So you're stating what you want to simulate, you're planning how you're going to do it, you perform repetitions of it, and then you can make a conclusion about it. So if we were trying to figure out the probability that a fair lottery would result in 2 winners from an AP Stat class, so we have students, so we have 95 students, so the AP Stat class is, their students labeled 1 to 28. The other class is 29 to 95. So we're going to ignore those labels there. So you're reading across here. So you're just picking 2 winners. So if I go across a line in the table, so they picked 139. So this was not an AP, this was not an AP, this was an AP, but not an AP, and this was not. So if we keep repeating this, you can kind of see that you don't hit having 2 AP students until this trial, and this trial. There's 18 trials here, so in 18 of those repetitions, 3 out of 18 times, we saw the winners being from both the AP Stat class, and so therefore the probability of them winning is 16.7%. And again here there was boxes of cereal boxes, and they were trying to get all these different cards. So they had, some of them had, they were equally distributed throughout the boxes of cereal. So Jeff Gordon was label 1, and then so on all the way down to Jimmy Johnson. And what's the probability that it would take 23 or more? So if they use the calculator here to simulate buying 1 box. So in this case, they used the calculator just 1 time, so it took 9 boxes. If they run another trial, it took 15 boxes. Another trial says it took 10 boxes. Another trial, so then they just keep going through it. They get all those trials and stuff like that. Then they can look at that to figure out what's the probability it takes 23 or more. As you can see here, maybe, I don't even know if those are 23. So they never had to buy more than 22 boxes. So yeah, they never got past that 23, so the probability it would take 23 or more boxes to get all of the cards is 0. In the next section, of Chapter 5, we started our probability adventures. So we started off with some rules here. So some definitions here. We had a sample space, so we defined that as S, and if you remember, I always use the brackets in class. It's the set of all possible outcomes. And the probability model consists of the sample space and the probability of each outcome. So let's talk about two dice. We have a red one and a green one. So these are the possible outcomes. So you could have one on the red and one on the green and so on. So there's 36 outcomes in total. Each of these outcomes has a 1 over 36 chance. So I could create a probability model with that. Some other definitions we had. An event is any collection of outcomes from some chance process. So an event is a subset of the sample space. So in like the last one, I could say what's the probability? You would get a 2 on the red and a 3 on the green. So that is a event that happens in that sample space. We wrote things with P as the probability of A. We could also define the event as the sum is 5. So then these were all the scenarios that gave us a sum of 5. There was 4 of them, so 4 out of 36. We talked about something called the complement. So if we did the sum of not 5, we could do 1 minus 4 over 36, which would be 32 over 36, and that was the complement. So our rules here, the probability is always a number between 0 and 1. It could be 0 or 1. All outcomes together have a probability that adds up to 1. So in that dice example, 36 outcomes. Each outcome had a probability of 1 over 36. You add them all up, you get 1. If all outcomes of the sample space are equally likely, the probability that event A occurs can be found using this formula. Then that complement rule, the probability that an event does not occur is just 1 minus the probability. And then if two events have no outcomes in common, so if there's nothing in common, then they're said to be mutually exclusive, and the probability that one or the other occurs is the sum of their individual probabilities. So we just added them up. So this is everything kind of in mathematical notation. There's your complement rule. This is the notation your textbook uses. And then the addition rule for mutually exclusive. So if you're doing A or B, you're just adding the probability A plus the probability B. And you can read through this example if you want. They just question if it's a legitimate one, and then they found a probability. Just if you're asked any probability questions, like on the free response, make sure you write out that probability statement and show what you're doing. Don't just write down an answer. All right, we also talked about two-way tables, and we made some Venn diagrams here. So in a two-way table, we have, in this one you have gender versus and pierced ears. So gender, male, female, pierced ears, yes or no. And we have two events here. So then we can find some of these probabilities. So the probability that they have pierced ears is just that 103 over the total. The probability that they're a male with pierced ears. So we want both of those things happening to the person. So being male and having pierced ears is 19 out of 178. Male or has pierced ears, I can't just add up the 103 over 178 plus the 90 over 178 because there's that overlap here. So we don't want to count them twice. So these are not mutually exclusive. So you can just add up the individual pieces and then divide that by 178. All right, and then this is what we were talking about with the Venn diagram. There was that overlap there. There was that 19 people right there that overlapped. So they're in that middle there of that Venn diagram. So we double count them if we just add the two circles together. So then we had a general rule that actually can apply to everything regardless of if it's mutually exclusive or not. So the probability of A or B can just be equal to the probability A plus the probability B minus the probability of A and B. And then just some standard vocabulary here. When you're drawing a circle, this is A, everything outside of A is A complement. If you had two events, if they had nothing in common, they are mutually exclusive. Here's A, here's B. This is the sample space on the outside, so there's no overlap there. There's no outcomes in common. This one, if you're talking about the intersection, so you're talking about A and B, so they're happening to both, like to one person. There's some that's what they have in common. If you're talking about the union, so they're talking about everything, the union of A and B, then it's all of this and all of this. Again, you don't want to double count that section. To keep it straight, U for union, and then this and symbol is for intersection. So then this table looks like this with the Venn diagram. Remember, A is the being male, B is having pierced ears. There's those, so that 4 out there is the females that don't have pierced ears. There's some notation here that you can kind of look at to remember what some of that is. So just the big thing is remember with your overlap. All right, and I'm going to do the second part of chapter 5 in another